Hello, Brickheads. Welcome to FRQ number 5, 2017. Probably just got beat down on number 4, and then in walk number 5, and it looks pretty ugly when you look at it. But it's actually really straightforward. It's a particle movement problem that involves knowing when the velocity is positive, it's going to the right, and when the velocity is negative, it's going to the left. It involves you're given the position function, and start with that, and then on another particle you're given the velocity function and start with that. So that's it. There's a little bit of speeding up. Remember, speeding up is when your velocity and your acceleration match in signs. If I'm headed in the negative direction with velocity and I'm accelerating in the negative direction, I speed up. But if either of those two is opposite of each other, I'm doing that up here. So if they're both headed in the same direction, awesome. The second that one of them goes the other way, that's when you slow down. All right? So let's talk about this one. It says two particles are moving along an x-axis from 0 to 8. So I'm only talking about the first 8 seconds of this particle motion. It gives me a function for particle p in terms of this natural log. And then it gives me a particle q, but it gives me the velocity of particle q. So this is a position function and this is a velocity function. And it also gives me that particle q has an initial position of 5 when t equals 0. That tells me I am going to have to use an initial condition. I am going to be integrating this velocity at some point to produce a position function so I can use this data right here. So I know that's coming. All right, part A. So part A says, for the first 8 seconds, find out when this is moving left. So if I'm going to figure out where something is moving left, I need to know when the velocity, which is x prime of t, is less than 0, right? So when it's less than 0, then this thing is moving to the left. So if this is my function right here, if I have this function, I'll just do this work for you here. So if x for p is the ln of t squared minus 2t plus 10, then x prime, the velocity function, is going to be 1 over all of that, t squared minus 2t plus 10, and then chain rule 2t minus 2. That's not supposed to be there. So 2t minus 2. So I can rewrite this as, on top, 2t minus 1s, that's factored, over t squared minus 2t plus 10. And my job is to try to figure out, hey, when is this x prime function, when is this velocity function going to be positive, and when is it going to be negative? So I have 2 chunks to it. I can see that I'm definitely going to have a critical point at 1. I'm going to have to look at t equals 1. But what about the bottom? Like, where are the critical points on the bottom? Well, here's the thing. If I looked at this bottom part, it doesn't have any zeros. This thing never goes below 0. I mean, think about it. This is a graph of a parabola. Just the bottom part would be a parabola. If I asked you to graph t squared minus 2t plus 10, so if I asked you to graph that, it would have a y-intercept of 10, and it's a t squared function. It's never going to get down here. As a matter of fact, the vertex is going to be at negative b over 2a. The vertex is going to be at 1. It's going to go down like this, and then it's going to turn around and go up. So I don't even have to worry about the bottom of this fraction. The only one I have to worry about is when t equals 1. Because the bottom of this will never be negative. It's always greater than 0. If you don't believe me, pick a number for t and plug it in. You'll get a positive number. All right, so anytime t is a giant positive number, it's plus. Anytime t is a negative number, or a less than 1, like 0, it would be negative. So it's very clear that anything on this side of 1, it's going to be negative and moving to the left. So anywhere from 0 to 1. So let's see what they have over here for their solutions and their points. So part 1, here we go. Whoa. All right, so part 1, there's my derivative. There's my factored form. They don't have any glorified explanation. They just say, dude, this is always bigger than 0, accept it. So you can do b squared minus 4ac, find the discriminant. or you can graph it and think about it. They don't ask how you know, as long as you know. And then I know that the derivative is going to be worth, what does it say here? X prime of t equals 0 and t equals 1. Yes, we know that. That is called a critical value. Therefore, the particle is moving left from 0 to 1. So you get 1 point if you have the correct derivative, and you get 1 point if you have the interval from 0 to 1. Okay? So part B. Part B is a little bit more straightforward. Part B says, hey, let's do something similar for particle Q, but we're going to figure out when are the two particles moving in the same direction. So I need this graph for particle P, and then for particle Q, I need another graph. But this one's going to be a little easier because it gives me the velocity function. So all I need to do is solve this velocity function, right? So the velocity function for Q is t squared minus 8t plus 15. That's t minus 3 and t minus 5. So at 3 and 5, this is the worst number line ever, I have two critical values. Yeah. So at 3 and 5, I have two critical numbers right there. So if t is a super positive number, this is going positive direction. So anything above 5 is positive. Anything between 3 and 5, like 4, that would be positive and that would be negative, so it's negative. And then anything before 3, these would both be negative, so this would be positive again. So it's going to say, hey, when are they traveling in the same direction? So you can see on this number line, from 5 to 8, leave these ones, and then it's positive from 1 to 3. So those should be the numbers that we see in our problem over here. So here we go. I do like their number lines. They're actually way better than mine because they're made with computer, and they're also correctly spaced, unlike my garbage number lines. However, there they go, basically the same. And where do they match up? They match up from 1 to 3, that's what we said on the other paper, and from 5 to 8, that paper also. So you get a point for having the intervals, and you get a point for this analysis using v prime of t, which I believe would be all of this stuff here. Okay? All right. Question C. 4 parts to this, brutal. Question C. Question C says, hey, do me a favor, find the acceleration of particle Q at 2, and then tell me, is the speed increasing, decreasing, or neither? So now I need to compare velocity and acceleration. So it's a super easy, to find the acceleration, because remember, if the velocity is t squared minus 8t plus 15, I could just find the derivative of that. I get 2t minus 8. So here we go. Part 5, we have 2t minus 8. There's my 2t minus 8, which means I have a critical number at 4. I don't know why they don't have that information there. Huh. That's funky. All right, whatever. I don't know. It said to evaluate it at t equals 2, so they plugged in a 2. 2 times 2 minus 8 is negative 4. So that's the acceleration. So the acceleration at 2 is going to be negative 4. You get a point for that. And then it says, is the speed or decreasing or increasing at 2? Well, the acceleration is negative. So is the velocity negative? So if I plug a 2 into the velocity equation, what do I get? So I go back to find my velocity equation. So velocity was t squared minus 8t plus 15. So v of 2 equals 4 minus 16 plus 15, which turns out to be 3. So since the velocity is positive, right, and the acceleration is negative, those are the opposite. So since they have opposite signs, then the speed is decreasing, right? So it's slowing down, right? Its speed is decreasing. You get a point for saying all that stuff. All right, last chunk. Here's my integration part. I haven't done it yet. It says find the position of particle Q for the first time it changes direction. So I'm going to have to integrate particle Q, that's my original particle Q, and then plug in my initial value. So remember, it gave me an initial value. It said X for Q of 0 is worth 5. So it actually gave me that point of 0, 5 on my function. So I'm going to integrate that and then plug in a 0, 5 to find C. So actually I'm going to, what does it say? Find the position of the particle the first time change directions. All right, never mind. Let me rephrase that. I got to read the whole question. So the first time that particle Q changes directions is right here, right? It says it changes directions. It goes from moving in the positive direction to moving in the negative direction. So when the velocity changes from positive to negative, so at time equals 3, that's the one that I'm really looking at. What's happening at time equals 3? Okay, find the position at time equals 3. So there we go. So particle Q first changes direction at time equals 3. So they're like, hey, where is it? Find the position of that particle at time equals 3. Well, the position at time equals 3 is going to be the initial value where it started plus how far did it go from 0 to 3, right? So basically, I'm going to find the integral of this, and then I'm going to add the initial position, which is just the c. So it's giving me the same thing. So the integral of this v of t, well, here's v of t. So I need to find the integral of t squared minus 8t plus 15. That's this. And then I need to go from 0 to 3. So when I plug zeros in, everything disappears. So all I'm going to do is plug the 3's in, and I get that. And my initial position is 5. So my grand total is going to be a total movement of, I'm going to end up, at 23. So it's going to move 18 spaces over to get to 23. So you get a point for the antiderivative. That is this guy. You get a point for using the initial condition. That's this guy. And you get a point for the answer. That's that guy. Whew, brutal. Catch you next time.